Welcome to Boring Lectures. We know sleep doesn't always come easily. That's why we're here. This podcast is deliberately and delightfully dull. Each episode takes a genuinely interesting scientific topic and presents it in the most methodically detailed, soothingly repetitive, and gently monotonous way possible. Our goal is simple: to help you relax, let go, and drift peacefully off to sleep. Tonight, we'll be exploring the life cycle of an ordinary star. We'll move through it slowly, calmly, without drama or urgency. If you'd like more calm lectures like this, you can follow Boring Lectures in your podcast app. And, when you're not about to fall asleep, leave a rating or review. It quietly helps the show reach others who might need a gentle way to drift off. For now, settle into a comfortable position. Adjust your pillow. When you're ready, you can close your eyes or simply soften your gaze. We hope you're bored. To sleep. Let us begin our examination of the life cycle of an ordinary star. We will proceed methodically through each phase, considering in detail the physical processes, the timescales involved, and the transformations that occur as a star moves from birth to its ultimate fate. The journey of a star begins not with the star itself, but rather with a giant molecular cloud. These clouds are enormous accumulations of gas and dust in interstellar space. A typical giant molecular cloud has a diameter of approximately 100 light-years. To express this in more familiar units, 100 light-years corresponds to about 9.5 multiplied by 10 to the 14th kilometers. The mass contained within such a cloud can reach up to 6 million solar masses. This quantity is equivalent to 1.2 multiplied by 10 to the 37th kilograms. These molecular clouds consist primarily of hydrogen gas and helium. There are also small quantities of heavier elements present. Additionally, dust grains are mixed throughout the cloud. As the cloud undergoes gravitational collapse, it breaks into smaller and smaller pieces. This fragmentation process continues until individual fragments form that will eventually become individual stars. The timescale for molecular cloud formation varies depending on specific conditions within the cloud. Recent studies have examined colliding flows of gas. These studies reveal that star formation can begin after approximately 4.4 million years in the case of rapidly moving flows. In the case of slower moving flows, star formation begins after roughly 16 million years. Cloud formation occurs when two flows of gas collide. This collision creates a thermal instability. The thermal instability produces a dense, cold layer of gas. This layer contains significant turbulent substructure. Initially, the small-scale structure in this cold layer is not self-gravitating. Eventually, however, some small dense regions become gravitationally bound. These regions then enter runaway gravitational collapse. This collapse leads to the formation of stars. The time required for different molecular species to appear during cloud formation varies. Regions showing high molecular hydrogen fractions appear early in the cloud's evolution. These regions can persist for considerable periods before the onset of star formation. High carbon monoxide fractions, by contrast, only appear within self-gravitating gas. This occurs around 2 million years before the onset of star formation. The gravitational collapse of a molecular cloud fragment represents the initial stage in stellar formation. As the cloud fragment collapses under gravitational attraction, the material at the center becomes increasingly hot and dense. the collapse is never entirely uniform. Rather, the fragment typically has some initial rotation. Alternatively, it acquires rotation during the collapse process. The conservation of angular momentum means that as the fragment becomes smaller, it rotates faster. This principle is similar to a figure skater spinning faster when pulling in their arms. This rapid rotation causes the collapsing cloud to flatten into a disk shape. Most of the mass becomes concentrated toward the center. Once gravitational collapse has begun in earnest, the collapsing cloud fragment becomes known as a protostar. The protostar represents an intermediate stage. It exists between the initial molecular cloud and the fully formed main sequence star. During the protostellar phase, the object continues to grow. It grows by acquiring mass from its surrounding envelope of interstellar dust and gas. The physical conditions in the protostellar core change substantially during contraction. The temperature increases. The density also increases. By the time a collapsing gas cloud has become a protostar, its core has reached temperatures of several million kelvins. At these temperatures, hydrogen in the core exists as a plasma. A plasma is a state of matter consisting of hydrogen ions, free electrons, and other charged particles. These particles move at extremely high speeds. The growth of a protostar occurs through a process called accretion. Accretion is the process by which the protostar captures material from its surrounding disk and envelope. Material from the disk falls inward. As it falls toward the protostar, it gains kinetic energy. When this material strikes the surface of the protostar, the kinetic energy is converted into thermal energy. This conversion occurs through accretion shocks. The accretion shocks heat the stellar surface to extremely high temperatures. The energy generated through accretion shocks on the protostellar surface represents the primary luminosity source during the early protostellar phase. As the accretion process continues, the protostar grows more massive. The internal temperature rises even further. This temperature increase is due to gravitational compression. The properties of protostars vary substantially. The variation depends on the ultimate mass the star will attain. For low-mass protostars destined to become red dwarfs or sun-like stars, the protostellar phase lasts a considerable time. This phase can last millions of years. During this time, material slowly accumulates onto the growing star. For higher-mass protostars, the accretion process occurs much more rapidly. Consequently, the protostellar phase is correspondingly shortened. The maximum possible radius that a protostar can achieve can be estimated. This estimation uses the virial theorem and stellar structure equations. For a solar mass protostar, the theoretical maximum radius has been calculated. This radius is approximately 36 solar radii. This calculation assumes all the internal energy of the star is released as the cloud contracts. However, observed sizes of young stars, such as T Tauri stars, are generally found to be significantly smaller. They are smaller by approximately an order of magnitude. This suggests that significant energy loss occurs during the protostellar contraction. The protostellar phase typically lasts for millions of years. The exact duration depends on the mass of the forming star. It also depends on the rate at which material accretes onto its surface. For solar mass stars, the protostellar contraction phase can last approximately 50 million years. This is the time before the star reaches the main sequence. For higher mass stars, the contraction phase is substantially shorter. A 3 solar mass star might reach the main sequence in only 2.5 million years. For lower mass protostars, the timescale extends considerably. A 0.5 solar mass red dwarf may require 160 million years to reach the main sequence. An important process occurring during the protostellar phase involves the fusion of deuterium. Deuterium is a rare isotope of hydrogen. It contains 1 proton and 1 neutron. When the core temperature of the protostar rises above approximately 1 million kelvins, deuterium fusion can occur. Deuterium is sufficiently rare that this fusion process does not generate substantial energy. It certainly generates far less than hydrogen fusion. Nevertheless, it can provide some energy generation. The lowest mass objects in the stellar mass range are capable of deuterium fusion. Objects below approximately 0.08 solar masses never reach core temperatures sufficiently high for even deuterium fusion to occur. Consequently, they are classified as brown dwarfs rather than true stars. As the protostar contracts, its core temperature increases beyond the deuterium burning temperature. However, it remains below the hydrogen fusion temperature of approximately 10 million kelvins. During this time, the star enters the pre-main sequence phase. During this phase, the star continues to contract under gravity. The gravitational energy released by contraction provides the luminosity of the young star. This phase lasts for millions of years. The duration depends on stellar mass. In this phase, stars are powered by gravitational contraction rather than hydrogen fusion. The pre-main sequence objects are classified according to their mass. Objects with fewer than 2 solar masses and currently undergoing contraction are classified as T-Tauri stars. More massive objects between 2 and 8 solar masses are classified as Herbig AE/B stars. The transition from the pre-main sequence to the main sequence occurs when the core temperature rises sufficiently to initiate nuclear fusion of hydrogen. For stars with masses similar to or less than the Sun's mass, the critical temperature is approximately 10 million kelvins. At this temperature, the thermal motion of hydrogen nuclei becomes sufficiently vigorous. The hydrogen nuclei are also called protons. They can overcome the electrostatic repulsion between the positively charged nuclei. When 2 protons collide at such high velocities, they can fuse together. This fusion forms deuterium and releases energy in the process. This initiation of hydrogen fusion marks a crucial transition in stellar evolution. Prior to this point, the star's luminosity is powered by gravitational contraction. Once hydrogen fusion begins, the fusion reactions provide outward pressure. This outward pressure counteracts gravity. The result is a state called hydrostatic equilibrium. In hydrostatic equilibrium, the star achieves stability. Hydrostatic equilibrium represents a condition in which the outward pressure generated by nuclear fusion reactions in the stellar core precisely balances the inward force of gravitational compression. The pressure generated by fusion reactions is transmitted outward through the stellar material. This transmission occurs in the form of photons, which are light particles. It also occurs through the thermal motion of particles. This outward pressure pushes against the weight of all the stellar material above it. This pressure supports the star against gravitational collapse. Should the fusion reaction rate decrease for any reason, the star would begin to contract under gravity. This contraction would raise the core temperature and pressure. The increase in temperature and pressure would thereby increase the fusion reaction rate. Conversely, if the fusion reaction rate increases excessively, the resulting increase in pressure would cause the star to expand. The expansion would cool the core. The cooling would decrease the fusion rate. This self-regulating mechanism maintains the star in hydrostatic equilibrium. This is a stable state that can be maintained for billions of years. The onset of nuclear fusion leads relatively quickly to hydrostatic equilibrium. This allows the star to evolve rapidly to a stable state. The star can then begin the main sequence phase of its evolution. In stars with masses comparable to or less than the Sun's mass, the primary mechanism for converting hydrogen into helium is called the proton-proton chain reaction. This is sometimes abbreviated as the PP chain. This process constitutes a multi-step sequence of nuclear reactions. In this sequence, 6 protons ultimately fuse together to produce 1 helium nucleus and 2 protons. The PP chain begins when 2 protons collide and fuse together. This fusion forms deuterium. Deuterium is a nucleus consisting of 1 proton and 1 neutron. The reaction also releases a positron. A positron is the antimatter partner of the electron. An electron neutrino is also released. The deuterium nucleus produced in this initial reaction can then collide with a 3rd proton. This collision results in fusion to form helium-3. Helium-3 is a light isotope of helium. It contains 2 protons and 1 neutron. A gamma-ray photon is released during this process. 2 helium-3 nuclei can then collide and fuse together. This produces 1 helium-4 nucleus. Helium-4 is the normal, stable form of helium. It contains 2 protons and 2 neutrons. 2 protons are released during this final step. The net result of this multi-step process is that 4 protons are consumed. They are converted into 1 helium-4 nucleus. 2 positrons and 2 electron neutrinos are released. The mass difference between the initial and final states of the PP chain reaction is responsible for the energy release. The mass of 1 helium-4 nucleus is slightly less than the combined mass of 4 protons. This mass difference is called the mass defect. The mass defect is converted into energy. This conversion follows Einstein's famous equation E = mc². In this equation, E represents energy. M represents the mass converted to energy. C represents the speed of light. The speed of light squared is an extraordinarily large number. It is approximately 9 multiplied by 10 to the 16th square meters per second squared. Even though the amount of mass lost in the PP chain reaction is minute, the energy released is prodigious. The mass loss is approximately 0.7% of the original hydrogen mass. Each time the proton-proton chain creates 1 helium nucleus, the energy released is approximately 26.7 mega-electron volts. Since stars contain immense quantities of hydrogen, vast numbers of these fusion reactions occur in stellar cores every second. In the case of the Sun, approximately 500 million tons of hydrogen are converted into helium each second. This conversion generates the measured luminosity. The rate at which the PP chain reaction proceeds depends critically on temperature. At the core temperatures of the Sun, the PP chain reaction proceeds at a rate that sustains the Sun's current luminosity. The Sun's core temperature is approximately 15 million degrees Celsius. This is equivalent to 27 million degrees Fahrenheit. However, the PP chain reaction rate is not a simple linear relationship with temperature. Rather, it increases approximately with the 4th power of temperature. This strong temperature dependence means that small changes in core temperature lead to substantial changes in the fusion reaction rate. Once a star establishes stable hydrogen fusion in its core and achieves hydrostatic equilibrium, it enters the main sequence phase of its evolution. A newly formed star will sit at a specific point on the main sequence in the Hertzsprung-Russell diagram. Its position is determined primarily by the mass of the star. More massive stars appear in the upper left portion of the main sequence. They are hotter and more luminous. Less massive stars appear in the lower right portion. They are cooler and dimmer. Small, Relatively cold, low-mass red dwarfs fuse hydrogen slowly. They will remain on the main sequence for extraordinarily long periods. This period can potentially last hundreds of billions of years or longer. Conversely, massive, hot O-type stars will leave the main sequence after only a few million years. A mid-sized yellow dwarf star, such as the Sun, will remain on the main sequence for approximately 10 billion years. The Sun is thought to be currently in the middle of its main sequence lifespan. Approximately 4.6 billion years of life have already passed. Approximately 5 billion years remain. The total duration of the main sequence phase for any given star depends fundamentally on the mass-luminosity relationship. This relationship is observed for main sequence stars. The luminosity of main sequence stars is directly related to their mass through a power law relationship. Luminosity is proportional to mass raised to the 3.5 power. More massive stars must have higher core temperatures. These higher temperatures are needed to establish the pressure needed to support their greater weight against gravitational collapse. At higher temperatures, nuclear fusion proceeds much more rapidly. This causes more massive stars to shine much more brilliantly. The lifetime of a star can be estimated by considering that the amount of available fuel is proportional to the star's mass. Meanwhile, the rate at which fuel is consumed is proportional to the star's luminosity. Consequently, the lifetime is roughly proportional to the mass divided by the luminosity. This gives a relationship where lifetime is proportional to mass divided by mass raised to the 3.5 power. Equivalently, lifetime is proportional to mass raised to the negative 2.5 power. This means that more massive stars live dramatically shorter lifetimes relative to their total fuel supplies. A star with 10 times the Sun's mass has a main sequence lifetime roughly 316 times shorter than the Sun's. It is not 10 times shorter, but 316 times shorter. The main sequence phase of a star's life ends when the hydrogen supply in the stellar core becomes depleted. The exact timescale for this hydrogen exhaustion depends on the stellar mass and the initial composition. For a solar mass star, it occurs after approximately 10 billion years. As the hydrogen in the core is consumed by fusion reactions and converted into helium, the core slowly becomes enriched in helium and depleted in hydrogen. At the point where nearly all the hydrogen in the core has been fused into helium, the core loses its primary energy source. Without the outward pressure generated by hydrogen fusion to counteract the force of gravity, the core begins to contract under gravitational attraction. The contraction of the hydrogen-exhausted core has important consequences. As gravitational potential energy is released through contraction, the core becomes hotter and denser. This heating causes hydrogen fusion to ignite in a shell surrounding the core. Hydrogen just outside the depleted hydrogen core reaches temperature sufficiently high to begin fusing. The onset of hydrogen shell burning produces more energy than was being generated by core hydrogen burning in the latter stages of the main sequence. This is because hydrogen fusion proceeds faster at higher temperatures. This increase in energy generation is more than sufficient to support the star against gravitational collapse. However, the additional energy has an important consequence. It causes the outer layers of the star to expand and cool. This phenomenon is sometimes called the mirror principle. The physical mechanism operates as follows. Hydrogen shell burning generates energy that heats the material just above the burning shell. This increased heating increases the pressure in the layers above the shell. The increased pressure can no longer be supported by the weight of the overlying material. So those layers move outward, As the outer layers expand, they cool. This cooling is due to the conversion of gravitational potential energy into expansion. The cooling of the outer atmosphere means that the photospheric opacity increases. The outer layers become more opaque to radiation. This causes the luminosity of the star to increase dramatically. The transition from the main sequence to the red giant branch is gradual. It passes through an intermediate phase called the subgiant branch. The subgiant branch is populated by stars that have depleted the hydrogen in their cores. They have transitioned to hydrogen shell burning. However, they have not yet reached the rapid luminosity increase characteristic of full red giants. During the subgiant phase, the core continues to contract. The helium core grows in mass as hydrogen shell burning adds material to it. The temperature of the core increases gradually. Meanwhile, the envelope expands and cools. For a solar mass star, the subgiant phase lasts for a few billion years. This is a substantial duration. However, it is still only a small fraction of the total main sequence lifetime. Once the star reaches the red giant branch proper, it undergoes remarkable transformations in size and luminosity. The defining characteristic of a red giant is that hydrogen fusion continues in a shell surrounding an inert helium core. The core continues to contract and heat under gravity. Meanwhile, the hydrogen-burning shell releases energy at an ever-increasing rate as it becomes hotter. This continued energy release from the hydrogen shell provides the luminosity of the star, but simultaneously it drives expansion of the outer layers. The star expands to enormous dimensions. Its radius can reach up to 400 times the original main sequence radius. The Sun, if it were to evolve to the tip of the red giant branch, would expand to approximately 256 times its current size. This is about 1.19 astronomical units in radius. As the star expands, its surface area increases tremendously. This increased surface area radiates the substantial luminosity being generated by the hydrogen-burning shell. The surface temperature of the expanding star decreases. This is because although the star is generating energy at a furious rate, this energy is being radiated from an enormously expanded surface. The resulting change in temperature causes the star to glow redder than it did on the main sequence. The peak of the thermal radiation curve shifts to longer, redder wavelengths. For stars with masses less than approximately 2 solar masses, including our Sun, an extraordinary event occurs once the helium core reaches a temperature of approximately 100 million kelvins. At this temperature, the triple alpha process can begin. The triple alpha process is a fusion reaction converting helium into carbon. However, in low-mass stars, the helium core has become so dense that it is composed of degenerate matter. Degenerate matter is a state where the quantum mechanical pressure of electrons supports the matter against further gravitational collapse. This pressure is called electron degeneracy pressure. In degenerate matter, a crucial property emerges. The pressure does not increase with temperature in the normal way. Normally, heating a gas increases its pressure. This is due to the increased kinetic energy of particles. In degenerate matter, however, the electrons are already packed as densely as possible. This packing follows the Pauli exclusion principle. Heating does not increase the pressure. This unusual property of degenerate matter leads to an unstable situation once helium fusion begins. When the degenerate helium core is heated to the temperature required for the triple alpha process, fusion reactions begin and release energy. This raises the temperature further. Normally, this temperature increase would increase the pressure. The increased pressure would cause the gas to expand and cool. The cooling would reduce the fusion rate. However, in degenerate matter, the pressure does not increase significantly with temperature. So the increased temperature causes the fusion reaction rate to increase without producing the compensating pressure increase. This leads to a runaway reaction. Higher temperature causes faster fusion. Faster fusion generates more heat. More heat further raises the temperature. Higher temperature accelerates the fusion rate even more. This runaway helium fusion event is called the helium flash. During the helium flash, which lasts only a few minutes, the energy output reaches approximately 100 billion times the normal energy production of the star. The entire degenerate helium core erupts in simultaneous fusion. The rate produces energy comparable to the luminosity of an entire galaxy. However, this enormous energy release does not cause the star to brighten noticeably at the surface. Instead, the energy released during the helium flash goes entirely into expanding and heating the helium core itself. This expansion lifts the degeneracy of the electrons. As the core expands in response to the energy input, the density decreases. The temperature of the core changes. The core transitions from degenerate to normal, non-degenerate matter. At this point, the normal feedback between temperature and pressure is restored. After the helium flash, the star's structure changes dramatically. With the core now non-degenerate and stable, helium fusion can proceed quietly and continuously in the core. Rather than in a runaway flash, the fusion is now stable. The star's surface rapidly cools and contracts in response to the energy redistribution within the star. The radius reduces to approximately 2% of its giant radius. The luminosity similarly reduces. This reduction in size and luminosity represents a transition to the horizontal branch phase of stellar evolution. Once the helium core has been stabilized and is no longer degenerate, helium fusion can proceed steadily in the core of the star. The primary fusion reaction converting helium into heavier elements is the triple alpha process. In this process, 3 helium-4 nuclei are converted into 1 carbon-12 nucleus plus energy. The triple alpha process actually consists of 2 steps. 2 helium nuclei first combine to form beryllium-8. Beryllium-8 is highly unstable. It normally decays back to helium almost instantaneously. The half-life is only 8.19 times 10 to the negative 17th seconds. However, within this vanishingly short time frame, a 3rd helium nucleus can fuse with the beryllium-8 nucleus. This forms an excited state of carbon-12, called the Hoyle state. The energy released by the triple alpha process is approximately 7.275 mega-electron volts per carbon nucleus formed. In addition to carbon production, some carbon nuclei can fuse with additional helium nuclei. This forms stable OXYGEN16 and additional energy. The combination of these reactions produces the primary elemental composition of the post-helium burning core. This composition consists of roughly equal quantities of carbon and oxygen. The energy output from helium burning at the core is sufficient to support the star against gravitational collapse. This establishes a new hydrostatic equilibrium. The star now has 2 sources of energy. These are helium fusion in the core and hydrogen fusion in a shell surrounding the core. The core helium burning phase of evolution is called the horizontal branch. It is named because stars in this phase lie on a nearly horizontal line in the HR diagram of many star clusters. The horizontal branch phase lasts for a much shorter time than the main sequence or red giant branch phases. For a solar mass star, core helium burning lasts approximately 120 million years. This is roughly 1% of the main sequence lifetime. This drastically shortened duration reflects the much higher luminosity of helium-burning stars compared to hydrogen-burning stars of the same mass. After the core helium has become substantially depleted and begins to consist primarily of carbon and oxygen, the energy production from core helium fusion declines. Once again, without a primary energy source, the core begins to contract under gravity. The contraction of the carbon-oxygen core causes the temperature to rise. However, the temperature does not rise sufficiently to initiate carbon fusion in low and intermediate mass stars. Instead, helium fusion is reignited in a thin shell surrounding the now inert carbon-oxygen core. Simultaneously, the heating caused by core contraction causes the hydrogen-burning shell to expand outward and continue burning hydrogen. The star now has two sources of energy. These are hydrogen burning in an outer shell and helium burning in an inner shell. An inert carbon-oxygen core sits at the center. This phase of stellar evolution is called the asymptotic giant branch, or AGB. The name reflects the observation that in the Hertzsprung-Russell diagram, the evolutionary track of an AGB star approaches the original red giant branch track. However, it has higher luminosity. The AGB represents the final evolutionary stage of low and intermediate mass stars. This occurs before they eject their outer layers and become white dwarfs. During the AGB phase, the star expands to tremendous sizes. It sometimes exceeds the size, even of the red giant branch tip. The double shell structure of AGB stars is inherently unstable to thermal pulses. The thermal pulsation process occurs as follows. As the hydrogen-burning shell produces energy and deposits helium ash onto the helium-burning shell, the helium layer grows thicker and denser. Periodically, when enough helium has accumulated, the helium-burning shell undergoes a thermal runaway event. This is somewhat analogous to the helium flash in lower mass stars. During a thermal pulse, the energy output of the helium-burning shell can increase by a factor of approximately 1,000. This phenomenon is called a shell flash. These thermal pulses occur periodically. Intervals between pulses range from 10,000 to 100,000 years. This depends on the mass of the star. The thermal pulses temporarily reconfigure the interior of the star. This allows material rich in carbon to be dredged from the core to the surface of the star. This occurs through a process called convective mixing. After a few thermal pulses, the star becomes a carbon star. A carbon star is a star with more carbon than oxygen at its surface. This property can be observed in the stellar spectrum. During the final stages of the asymptotic giant branch phase, the expanded outer layers of the star become highly unstable and begin to pulsate. These pulsations in the envelope of the star can accelerate material to speeds approaching the escape velocity of the star. Working together with radiation pressure on dust grains, the pulsations cause the star to eject its outer layers into space as a diffuse cloud. The ejected material includes roughly 25 to 60% of the star's original mass. Meanwhile, the core contracts to form a white dwarf. The ejected material expands into space at velocities of approximately 20 to 30 kilometers per second. The compact remnant left at the center of the ejected envelope is the white dwarf. The white dwarf is extraordinarily hot. Surface temperatures initially reach approximately 100,000 kelvins. though the oldest white dwarfs cool to temperatures of only a few thousand kelvins. The intense ultraviolet radiation emitted by the hot white dwarf ionizes the atoms in the surrounding expanding gas cloud. Electrons freed by ionization subsequently recombine with the ions. This emits photons in the process and creates an emission spectrum. This ionized, glowing cloud of ejected stellar material is called a planetary nebula. When a low-mass star has shed its outer layers and formed a planetary nebula, only the core of the star remains. This is a white dwarf. A white dwarf is the electron-degenerate remnant of the stellar core. It consists primarily of carbon and oxygen in the case of solar mass stars. White dwarfs are extraordinarily compact objects. In terms of size, a typical white dwarf has a radius comparable to Earth. This is roughly 1% of the Sun's current radius. Yet, despite this Earth-size radius, white dwarfs contain nearly the entire mass of the original star. Typically, around 0.6 solar masses for a white dwarf produced from a solar mass star. This extraordinary density means that the density of white dwarf material is approximately 1 million grams per cc. Equivalently, this is 1 billion kilograms per cubic meter. A sugar cube-sized lump of white dwarf material would weigh approximately 2,000 kilograms on Earth. This is about 4,000 pounds. The properties of white dwarfs reflect the extraordinary densities of their material. At such extreme densities, the electrons are packed so closely together that they obey the quantum mechanical Pauli exclusion principle. No two electrons can occupy the same quantum state. This quantum mechanical pressure is called electron degeneracy pressure. This is what supports the white dwarf against gravitational collapse. It is not thermal pressure as in normal stars. Since the pressure is determined by density rather than temperature, the white dwarf can remain stable even as it cools over billions of years. The internal structure of a white dwarf is nearly isothermal. The entire interior maintains approximately the same temperature, initially around 100 million kelvins, but decreasing over time as the white dwarf cools. The cooling of white dwarfs is a remarkably slow process. A white dwarf has a very small surface area from which to radiate its thermal energy into space. So it cools gradually. It remains visible and detectable for an extraordinarily long time. As a white dwarf cools, its surface temperature decreases. The radiation it emits becomes redder. Its luminosity decreases. The oldest known white dwarfs still radiate at temperatures of a few thousand kelvins. This establishes an observational limit on the maximum possible age of the universe. Early theoretical calculations predicted that white dwarfs would cool at a certain rate. But observations revealed that white dwarfs cool more slowly than expected. The reason for this slower cooling involves the crystallization of the white dwarf material as it cools. When the interior of a white dwarf cools below approximately 10 million degrees Celsius, the material begins to crystallize. It transitions from a hot fluid to a solid crystal. This is similar to how water freezes into ice. The crystallization process releases latent heat. This has the effect of slowing the cooling rate. More massive white dwarfs cool more rapidly and reach the crystallization temperature in about 1 billion years. Less massive white dwarfs, closer to the mass expected for our Sun's eventual remnant, cool more slowly. They require up to 6 billion years to completely crystallize. The ultimate fate of our Sun provides an example of the evolution of a low-mass, solar mass star. The Sun is currently approximately 4.6 billion years old. It is roughly halfway through its main sequence lifetime. The Sun is expected to remain on the main sequence for approximately another 5 billion years. It will continue to fuse hydrogen in its core at a relatively constant rate. During its remaining main sequence lifetime, the Sun will gradually increase in luminosity. This occurs as the helium ash accumulates in the core. This causes gravitational contraction and an increase in core temperature. Approximately 4 to 7 billion years from now, when hydrogen fusion in the Sun's core diminishes to the point that the Sun is no longer in hydrostatic equilibrium, the core will undergo a marked increase in density and temperature. This phase change will cause the outer layers of the Sun to expand dramatically. This will transform the Sun into a red giant. The Sun's radius will expand to approximately 256 times its current value. This is about 1.19 astronomical units. At this enormous size, the Sun's outer layers may engulf the orbits of Mercury, Venus, and possibly even Earth. The Sun will spend approximately 1 billion years in the red giant phase. During this time, it will lose approximately 1/3 of its current mass through stellar winds. Eventually, the core will heat sufficiently to ignite helium fusion via the triple alpha process. The Sun will experience a helium flash approximately 1.2 billion years after the Sun leaves the main sequence. After the helium flash, the Sun will move to the horizontal branch. It will undergo quiet helium burning in its core for approximately 120 million years. After this phase, the Sun will evolve to the asymptotic giant branch. It will remain there for approximately 20 million years. The Sun will undergo rapid mass loss during the AGB phase. It will eventually eject approximately 90% of its mass. This will leave a white dwarf remnant containing only about 0.5 to 0.7 solar masses. The ejected material will form a planetary nebula around the white dwarf. This will create a spectacularly beautiful emission nebula. This planetary nebula will disperse within approximately 10,000 years. But the white dwarf remnant will continue to exist and cool for trillions of years. The Sun's ultimate fate is to become a white dwarf, a compact stellar remnant about the size of Earth, gradually cooling from initial surface temperatures of approximately 100,000 kelvins to eventual temperatures matching the cosmic background radiation temperature of only a few kelvins, completing its journey from hot, luminous young star to cold, dark stellar cinder. Thank you for spending part of your night with this episode of Boring Lectures. If this episode is helping you unwind, you might like to follow the podcast in your app. When you're rested, you can leave a short rating or review if you'd like. For now, just rest. Good night.